Hello everyone, this is Team Verve from Amrita Vishwavidyapeetham. We are Bhavesh, Krishna and Saragesh, and this is our innovation for the Tata Technologies Innovent, AeroTwin, an AGI digital twin MRO with explainable REL prognostics and federated fleet intelligence. So what we do, we catch aircraft failures before they can ground a jet, and we do it on a box that never touches the cloud. So it stays explainable and it works fully offline at the edge. So before I take you to my cloud console, let me just give you a small gist of all the issues happening right now. In airlines services still service aircraft on a fixed calendar. Every X flight hours, they do this check, no matter how healthy that specific tail actually is. So healthy jets keep getting pulled for checks they don't need, and quietly degrading ones fail between checks. A grounded aircraft costs up to 1.25 crores an hour. AeroTwin fix exactly what needs fixing and runs it on a 10,000 rupees Raspberry Pi completely offline. So let me take you guys to our cloud console. So this is our cloud console. So what you see here is four tails under twin management. So this is our entire morning screen at a glance. So we have a Raspberry Pi with 8 GB. We have local models running to be our co-pilots. We have an option to simulate cycles. We have the health of each flight. We have a crack in the 3D render. We have how much tails under each twin under each fleet. We have the status, how much we can go, how much we can be cautious about, and how much flights we should stop right now. And fleet health, overall fleet health of the entire fleet, how much tails need action right now, and how much money we save. So every tail is a real digital twin, a live 3D airframe, as you can see. So VTAXE is grounded. A 13 mm crack has appeared. So the skin tints with health, the glow reacts with clickable markers. So let's say we have four twins right now. Let's simulate our fleet. So 600 cycles, 1200 cycles. As you can see, the health degrades after each simulative cycle testing sequence. And so this is what we have to prevent. So the cycle runs and runs and runs until we have set a maximum upper cap of 12,000 cycles, and each cycle represents a trip. So how we do this? We sense, we predict, we feed it to the twin, we prescribe, we price ledger it, and we prove. So let's see what the fleet risk is. So this is the real core of the entire dashboard. So this is real data, 28,935 real generated aviation flights data from general aviations. So this is from the public NGA FIT dataset, recorded around 7,665 real unscheduled maintenance event. So these are all surprise events. So this is why this is a perfect dataset for our choice. So if you go for the scoring model, so if you see the risk is equal to 1 plus, so 1 plus days to event by 7 into, so this is our formula to find out what's the risk for each single aircraft we have. So right now we are processing around 7,065 maintenance events as issue types, and we have described them as pull forward, or we monitor, or we fly. So anything that has a lower cap of 40, or we are sure that the risk is not that much, we let them fly. Else we pull forward, and else we monitor. We monitor the flight 1 day before, 1 or 2 days before the maintenance event. So this is based on our deterministic explainable rule. So imminence is what is being meant here. Imminence times exposure is what results in the trained gradient boosted classifier. So we found no leakage and we measured the steps. So if we go to pull forward button, so we have the top row, we have around 109 or so intake, gasket, leak, damages, etc, 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 etc. So top of the list, so as you can see, we have 109. So what does it say? Flight 582 was pre-flight event of this episode. So we have recorded one intake gas leak damage. At least we took it 1 day before the maintenance event and 4 prior flights already in this pre-failure window. So this is how we save money. We pull flights in the pre-failure window and make sure not only we schedule them and fix them before the prior flights, we make sure we know what we're doing. We make sure all the data gets fed into the entire event. So what is actually going on? So we, in this data set, we have around 27 real-time sensors feeding values inside the deterministic explainable model. So what that is, so we have around all sensory data being recorded from multiple flights, and based on that we predict that what's going to happen right now. And from what has happened so far with these parameters and these unplanned unscheduled event such as these gas leaks, etc., etc., it's always better to know what's going to happen. So so this is our ML pipeline. So the inspection to decision model chain, this is what is running in our Raspberry Pi. So we detect, we size it, we find it, we grade it, we feed it to the twin, we forecast, we prescribe changes, and we price it back. We have one twin which is completely offline. So there is no cluster to load balance. So we're deducting that from a YOLO. So this is a serving path for crack detection as well. So this is not only, this is an extra feature in which we have. So we use a YOLO model to segment and detect cracks. We use RUCEO fiducial to establish an accurate sizable reading in millimeters. We grade it, we feed it to the twin, and we forecast and we prescribe. So the twin always needs to know what's each and every value inside it. So this is our architecture we have. So the training plan, we have version data, we transform it, we feed it to the leakage guard, we calibrate and we cover it. So we have something called as a promotion gate and registry. So for each validation harness, after the engineer sign off, we draft it and we sign it. So what this addresses is, for the full lineage chain, this makes sure nothing gets broken and nothing gets past the engineer sign off. So this is involving a human at runtime to make sure everything goes smoothly. And this makes sure that the system does not make completely autonomous issues on its own when, and it should always relies on the engineer sign off to be a plausible human to be accountable for this. So what is this edge runtime we have? So we quantize and recalibrate and we find the deterministic inference. So we have a twin, we band it, and we have a reason for it. So the rule baseline fallback establishes what is a baseline for each rule. Each aircraft has an SRM which represents what to do and what next. So from that we get a reason and etc., etc., etc. So let me show you what the model registry talks about. Crack segmentation, zero label anomaly, P10, P50, P90 is all probabilities of rule Paris. This is the rule Paris Monte Carlo simulation. So we have a Monte Carlo simulation of Paris law. So that allows us to establish the percentage of uncertainty. So this RUL is remaining utilizable life, and P10 and P50 is how much probability or how much probable that entire event is. We use Bayes to find per tail growth of each and everything that could happen, and we do it every scan. And this RUL, remaining usable life, or remaining usable life with Paris law, we do it at every 80% band and on targets. For the anomaly PC, we train it on normal data. And for crack segmentation, we recoil and then we use POD. So we log the quality as method and provenance. So, so this is our entire model registry runtime. So we have, so this is our entire runtime budget. So in latency, how much latency gets used by all these things. So after that, this is a feature drift monitor to make sure we don't go past what's necessary. So let's go to the audit trail. So the audit moves to the act and prove. So in the MRO Copilot box, so let's say, so these are all local models we're running. So in our, in my system right now, no model is running right now. No local models in Olama. So I'm going to invoke Llama 3.2, Llama 3.2, 3 billion parameter model. I'm going to ask it a question, let's say, which aircraft needs attention? Okay. So Olama will invoke it in instantly. So the get fleet summary is tool calling, agentic tool calling that we developed to feed the model and to know that it could access these tool calls at any time. So it got invoked and we got a response. So SRM limits for a crack at 8853, it will use tool calls we had made for it, and it will use citations as well. So since we don't have access to a proper SRM, we'll establish really soon, and we'll push it to the Git repository. So this is our edge telemetry metrics. So the last piece, the fleet gets smarter without any raw data leaving aside. So federative learning, not only federative learning, we have differential privacy noise as well. On every release, sites share protected aggregates. The four hangers labeled here are a labeled simulation. The fed average and privacy math is real though, but it all runs at the edge, offline, CPU only in milliseconds. And since everything is cloud AI is blocked in ITAR hangars, it's completely offline, and we can choose between local models as well. So if I ask which aircraft needs attention, now 5.3 model will get called. So let me go back to our console. AeroTwin turns fix on a calendar into fix exactly what needs fixing. Exactly when, we prove it and we price it. How? We sense, we predict, we decide, we price, we act, we prove and learn. And this is a closed loop happening on a 10,000 rupees completely offline box, which is the Raspberry Pi 8, Raspberry Pi 5, on real flight data with honest validation, and it prices every single decision in rupees. So in the cost section, we've we've arranged that we fed the numbers. Since each flight differs, you can add your own money per tail, etc., 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 and you can defer it, you can plan, you can replan, etc. So this will all be hosted soon, and we'll attach the link in our presentation for you to have a demo. Thank you.